Okay, today I want to talk about eigenvalues and eigenvectors of a square matrix. Okay, so the first thing we're going to start out here, let A be a square matrix. Now this time, this square matrix in the problems in this chapter will be either real or complex numbers. Okay, so we're not just sticking to real numbers in this chapter as we're going to see here. Okay, so we're going to bring the complex numbers in. But let's keep going here. Okay, so I've got a square matrix I'm calling A. If there exists, I should probably just have an S on the end. If there exists a scalar lambda and a vector v bar or x bar such that A times x bar is lambda times x bar. By the way, x bar has to be non-zero to be an eigenvector. Okay, then lambda is called an eigenvalue of A, and x bar is called an eigenvector associated with that lambda value. By the way, yes, this value is lambda. That's a little Greek L. Okay, lambda. Okay, alrighty. Now, what this means here is for an eigenvector and eigenvalue pair here, A times the vector x bar turns out to be just what? A scalar multiple of the original x bar. Okay, so when A acts as a linear operator on x bar, all it does is stretch or compress x bar. Okay, now this may look like a strange type of problem, but we're going to see this actually ends up being very useful in the end. Okay, right now we're just going to be kind of formal and introduce some examples and stuff, but then we'll apply it to several different types of problems later. Okay, so this actually comes from the German, by the way, eigenvalue. I think it meant like fundamental value. Okay? All right, so you've got, if it exists, okay? If it exists, lambda is called an eigenvalue, and you'll have an associated eigenvector. Okay, let's take a concrete example. Suppose A is the vector 3, 2, 4, 5, reading across there. Okay? Now I'm going to just pull this magically out of my hat. 3, 2, 4, 5 times this vector 1, 2. Just let me show you. Okay? If I go 3, 2, 4, 5 times 1, 2, then what I'm going to get is what? 3 times 1 plus 2 times 2. That gives me what? 7 here. And I'm going to have 4 plus 2 times 5. That's 14. Notice that's actually 7 times the vector 1, 2. Okay? So when A, that matrix acted on this vector 1, 2, what did it do? It just ended up multiplying it by 7. Okay? Now that usually doesn't happen, right? For other type of vectors, you can easily, if you just take some arbitrary vector, grab one, okay? What's going to happen here when it's multiplied on 3, 2, 4, 5, generally you're not going to just have a multiple of the original vector. It's just not going to work. Okay? But sometimes it does. And in that case, you're dealing with an eigenvalue eigenvector pair. Okay? So we would say here what? 7 is an eigenvalue for A. So that's a number. That's a scalar for A with associated eigenvector 1, 2. Okay? All right, so you see that? Okay, in the context of this up here. Okay, there's a concrete example. Now let me point this out. Note that any non-zero scalar multiple of a given eigenvector associated with a particular eigenvalue is also an eigenvector associated with that eigenvalue. Okay, well this is easy. Don't make this hard here. Suppose I come back up here. I've got the same matrix A, okay? But instead of 1, 2, I use maybe what? 2, 4, okay? Just the scalar, non-zero scalar multiple of 1, 2. So I've got 2, 4 here, okay? If I multiply that on here, I would actually get what? 14, 28, right? But that's still going to be what? 7 times my original vector 2, 4, okay? All right, so you see how that works? Did I emphasize this? I don't know if I did here. Okay, x must be a non-zero vector. Okay. By the way, you can say, let me come back here. I should say this anyways. X has to be a non-zero vector. Do you see if X is the zero vector, this would always hold here? This would be a pretty trivial equation. Okay. So we want our eigenvectors to be non-zero. Okay. That's what makes the problem special, as we'll see. Okay. All right. Now for the formal proof of my statement here, that I can take any eigenvector associated with an particular eigenvalue and multiply it by a non-zero scalar and still get an eigenvalue or eigenvector associated with that eigenvalue. Let's go ahead and assume that this has been satisfied. A times some x bar equals lambda times x bar for some lambda and x bar. Now let's suppose that A is any, I had here real scalar, but it could be complex in some situations. But A is some scalar, but it's non-zero, okay? Now I claim A times x bar is also going to be an eigenvector, okay, associated with lambda. And to prove that here, let's just go A times, I should say cap A times little ax, okay? So I'm multiplying these two together. Now, because little a is just a scalar, you know from multiplying matrices that I could actually bring that little scalar a right outside this product. So I've got little a times cap a x bar. Okay, you know that these two are equal here. Okay, no problem here. But wait a minute, cap a times x bar is actually supposed to be what? Lambda x bar, because of the equation above here. So I'm going little a times what? Lambda x bar, lambda being a scalar, a being a scalar, okay? But you know I've got what? Commutativity and associativity with the scalar multiples here. So this is actually what? Lambda times a x bar, okay? So now here, I've drawn these here. Look at the first and the last. A times what? Or cap a times ax bar has been what? Lambda times ax bar. So this means what? Ax bar is also an eigenvector associated with that eigenvalue lambda. Okay, let me throw this in here just real fast here. Things you will run into later in your lives if you continue your mathematical experience here. Some other names for eigenvalues are characteristic values. Sometimes you'll see here we have a characteristic equation. Okay, something you might also know from differential equations. Spectral values, okay, this is more advanced here. Spectrum, spectral theory. Yeah, spectral values, that's also a common name for eigenvalues, okay? Now let's talk about actually computing eigenvalues and finding the corresponding eigenvectors, okay? All right, first I'm going to start out here. Suppose x bar is an n vector, okay, a real n vector. Just what I made it here. Again, that could be complex. Okay, these could all be complex numbers, but I'm just going to say it's a real, a real vector. Okay, a real n vector. Let's go ahead and notice something real fast here. If I go any scalar lambda times x bar, I can actually write that as a matrix product in the following way. Well, wait a minute. That's lambda times x bar is lambda times I sub n x bar. What's I sub n? I sub n is what? The n by n multiplicative identity. So it would have what? Ones down the main diagonal, right? It'd be n by n with ones down the main diagonal and zeros everywhere else, right? Okay. If I took that and multiplied it by x bar, since x bar is an element of Rn, this just would give me x bar, right? Okay, since that's true, these two must be equal. Okay, but now I'm going to use the associative property that I have with multiplying matrices and scalars here. So I'm going to reassociate this product here, and I'm going to write it this way. That's actually lambda times I sub n, right? Lambda I times x bar out here. Okay, what would lambda times I be? If I go this vector, or no, I'm sorry, this matrix times lambda, I would just have what? I would have lambdas down the main diagonal, and then what? Zeros off the main diagonal. Okay, multiplying by x bar. So keep that in mind. Okay, because let's come back here. Let's suppose that A is n by n. Okay, then we have this equation, right, for eigenvectors and eigenvalues. Okay, ax bar equals lambda x bar. This could be rewritten in the following way then. Okay, as I just showed here, I could actually rewrite this way. Okay, now I dropped my subscript n here since it's contextual here. Okay, and this is usually done. But anyways, this is what? A x bar equals lambda I times x bar. And then I'm going to subtract lambda I x bar on both sides of this equation right here. Okay, so I get this equation right there. Ax bar minus lambda I x bar equals 0 bar, right? The 0 vector. And then you notice the common factor between these two. We do have distributivity in matrix multiplication, so I'm going to factor out that x bar here. And I've got A minus lambda in times x bar is the 0 vector. Okay, notice that this whole thing in parentheses, this is an n by n matrix. So I've shown you that there in red. That is an n by n matrix. This is an what? N by 1 matrix also. That's an n column. That's a column vector, right? Okay, and this is a column of zeros, n of them. Okay. Now, let me point out, look at this equation. This is equivalent to the original. Okay, these are saying the same things. This is saying the same thing as that, just in two different ways, right? Okay. Now, let me just point out here, if this matrix A minus lambda I were invertible, okay, that would mean I have a multiplicative inverse, then the only solution to this equation would be what? X bar equals 0, right? The 0 vector. X bar equals 0 bar. That would be the only solution. Why? Well, we could solve this equation above by multiplying on both sides on the left by what? The inverse on both sides, and we would isolate x bar on the left-hand side, but any matrix times what? The 0 vector is going to be the 0 vector, so we would draw this conclusion here, right? Okay. But well, we excluded this trivial solution, right? Remember, we didn't want our eigenvectors to be 0, the 0 vectors? Okay, so I'm excluding this. So it must be the case that what? A minus lambda I is not invertible. Okay, so we must have to get, to actually get eigenvectors, okay, we must have that this n by n matrix, A minus lambda I, is not invertible. Okay, some people will call that singular. Okay, all right, when is a square matrix going to be not invertible? Okay, well, you remember what? A square matrix is invertible if and only if its determinant is non-zero. Since I want it to be not invertible, that means its determinant must be equal to 0. Okay, so what I see here, the condition that lambda be an eigenvalue and with associated eigenvectors of A is that the determinant of A minus lambda I must be 0. Okay, so this is going to give us an equation that we can use to actually solve for eigenvalues and eigenvectors. Okay? All right, let's take a concrete example here. Okay, so I'm going to take a different A that I did the first example here. Find any eigenvalues of this 2 by 2 matrix, 3, -1, 2, 0, reading across, okay? So that's my A. Now, what's A minus lambda I? Well, the I has to be a 2 by 2, right? Okay, so this is what? 3, -1, 2, 0, minus lambda I would be what? Lambda, 0, 0, lambda, right? Okay, now if I take the difference between these two matrices, I get 3 minus lambda, -1, 2, and then minus lambda. So what I've really done is just come down the main diagonal and subtract lambda on both of those. Okay? On the main diagonal elements. Okay, do you see where that matrix came from? Okay, now what did I want? I wanted its determinant, right, to be 0 here. So I'm going to use the bar notation now. So I'm going to put vertical bars around that, and I'll go vertical bars, 3 minus lambda, -1, 2 minus lambda. and I want that to be 0. Let's go ahead and compute what this determinant is. That would be what? 3 minus lambda times minus lambda, subtract 2 times a negative 1, set that to 0. And we've got the following. This reduces down to lambda squared minus 3 lambda plus 2 is 0. And this factors easily, yes, this is a nice set problem. This factors easily into lambda minus 1 times lambda minus 2 is 0. Therefore, lambda equals 1 or lambda equals 2. Okay? So this matrix actually has 2 eigenvalues. Okay? 2 eigenvalues. Now, these are going to have associated eigenvectors, but I'm going to hold off on finding those. Okay? So I'll hold off on the eigenvalues. I want to make some comments before I do that, actually find the eigenvectors associated with this. This thing is sometimes called the characteristic equation, okay? The characteristic equation that is used to find the eigenvalues, okay? In the general case, if A is n by n, I want you to think about this, then the determinant of A minus lambda I is going to be a polynomial in lambda, okay, lambda the unknown, and it's going to have degree n, just like we had in this situation up here. This was what? A 2 by 2 matrix, right? A was a 2 by 2 matrix. We ended up with what? A polynomial equation of degree 2, okay? All right. We're going to take this and we're going to set it to 0. So the eigenvalues of an n by n matrix are the zeros of this characteristic polynomial, some people would call it, by the way. But this polynomial, characteristic polynomial, the determinant of A minus lambda I. Istic, okay? Cool. Now, back in college algebra, you learned something called the fundamental theorem of algebra. What did it say? Every polynomial in the complex numbers of degree n must have exactly n zeros. When I say complex numbers, that would include the reals, right? Just zero imaginary part. Must have exactly n zeros. Remember that? This is counting multiplicity, though, and allowing possibly complex zeros, okay? Thus, if A is an n by n matrix, then A has n eigenvalues, but that would be what? Counting multiplicity and allowing complex eigenvalues, okay? If you didn't want to allow complex eigenvalues, there are cases where there are no eigenvalues at all, okay? But if you are allowing complex eigenvalues, there's going to be n of them, but again, that would also be counting multiplicity, okay? If you need to review those ideas, go look in your old college algebra book, okay? All right, we'll be talking more about it anyway, but just for now. Now, let's go back to our previous problem here where we were looking for eigenvalues, and then I held off on finding the corresponding eigenvectors. Okay, let's go ahead and find those eigenvectors now. Okay, so this was our matrix A, 3, negative 1, 2, 0, reading across. Okay, this time now we had 2 eigenvalues. Okay, we had 1 and 2 as eigenvalues. I'm going to go ahead and use a subscript notation now with those. I'll say lambda 1, that's my first eigenvalue. That turned out to be 1. And my second eigenvalue turned out to be 2. Okay, now I'm going to take each case separately. If you don't want to use subscript notation, you can here. Skip it. But lambda 1 is 1. Let's go ahead and look at this. Remember what our problem, right? One way of looking at it was what? A minus lambda I times our eigenvector is the 0 vector. Okay, so that's the way I'm looking at it here. So here in red, I actually showed you where we're subtracting off this eigenvalue 1 here. So this is going to be what? Down the main diagonal, 3 minus 1, 0 minus 1. The off diagonal elements are not going to change, okay? Okay, so that's A minus lambda I, okay, for the particular lambda equals 1. Here's our eigenvector. I just had its components be x1 and x2, and there's a corresponding 0 vector there. And then I wrote it as an augmented matrix instead, okay? So this looks like good Gaussian elimination here. So I've got the x1 column here and the x2 column here. Notice that this is what redundant here, the second row. We're not going to, this has what, 2 rows? This is not going to have rank 2. It's going to have a rank less than 2, right? Because what? Otherwise it would be invertible and you'd have a unique solution, which is the 0 vector, which we don't want. Okay, in fact, remember, we're setting this up exactly to make sure we get eigenvectors that are non-zero. So anyways, when we subtract this off, we get 2, -1, 0, 2, -1, 0. Okay, the second row is redundant. So let's go ahead and just see what we conclude here. We would have what? This statement would be 2x1 minus x2 is 0. This would mean that what? 2x1 is x2. Okay, now our eigenvector was what? x1, x2, that's what we were calling it. So this is what? x1, 2, x1. So we could say what? I could bring out the x1 as a factor. It's x1 times 1, 2. Okay? Now, what am I going to use for my eigenvector? I'm going to use 1, 2. But notice that what? Remember my previous statement here? Any non-zero multiple of 1, 2 would also work. Okay? Any non-zero multiple of an eigenvector is still an eigenvector associated with that eigenvalue. And you can see that working right here. Well, I didn't ask for all eigenvectors under the sun associated with this particular eigenvalue. I just wanted one of them. Okay? So 1, 2 would be nice and convenient for me. Okay? So here I'm going to do what? This doesn't look very good, but that's lambda 1 is 1. The associated eigenvector, or unassociated eigenvector, I should say, is 1, 2. Let's just do a double check going back to our original definition. Okay, here's my original matrix, 3, -1, 2, 0. I'm multiplying it by the vector 1, 2. And you could see I would get what? 3 minus 2, and then what? 2 plus 0, just multiplying here. That would give me the vector 1, 2, which is 1 times my original multiple, or my original vector here, 1, 2. So you see that this is indeed the case, that 1, 2 is an eigenvector of this matrix with associated eigenvalue 1 here. Okay? Or you could reword that if you want. Okay? Lambda 2 is 2. Remember the other eigenvalue we found? Okay? Let's go ahead. Now I'm jumping straight to the Gaussian form here. Okay, make it a little easier. That's what I would do also when you're working these problems. It's okay in the beginning, writing it this way, getting you to understand this, but let's jump to this now. You guys get the idea, I assume. Okay, so there's 3 minus lambda, -1, 2, 0 minus lambda, lambda being 2. And then I got zeros on the other side. Okay, this goes to what? 1, 1, 2, -2, and zeros on the other side. You can see once again that the second row is redundant. Okay, alrighty. So this only has rank 1 is what would happen here. And you can see what this would conclude. We conclude x1 and x2 have to be equal. Okay, now the name of my eigenvector was v2, but I still said it was what? x1, x2. Okay, so but x2 is really x1, so that's x1, x1. I could factor out the x1. So it's the set of all eigenvectors are what? All multiples of 1, 1. All non-zero multiples of 1, 1, I should say. Scalar multiples. Okay? So lambda equals 2 with corresponding eigenvector 1, 1. Okay? So I'll just take a particular eigenvector there. And there we've got it. Okay? Let's go ahead and just before we leave here, let's check this, make sure it works. Okay, back to the original form. Here's my original matrix, 3, -1, 2, 0. Let's multiply that by 1, 1. Okay, you can see we've got 3 minus 2, and then what, or 3 minus 1 and 2 plus 0. And that would be what? 2, 2, which is really 2 times 1, 1. Okay, so you could see this is correct. 1, 1 would be an eigenvector of this matrix with corresponding eigenvalue 2. Okay? All right, just a little introduction to this. I hope you understood that. Okay? More later.